Alright, so this video is just reviewing key terms with acids and bases. Arrhenius acids and arrhenius bases have to have hydrogen ions and hydroxide ions present in the solution. Is probably the most narrow definition of an acid and a base. Arrhenius acids donate hydrogen ions while arrhenius bases accept them. The hydroxide allows us to accept them. So you see there the examples. How both acids have a hydrogen, H2SO4 happens to have two, that could be donated, while the hydroxide in the two metal bases, the lithium hydroxide and calcium hydroxide, would be able to accept them in an acid-base neutralization reaction. Bronsted-Lowry expanded the definition of an acid and base. It didn't really change the acids terribly much, it just calls them now proton donors. So they just have to be able to donate a proton, and typically that too is still in the form of a hydrogen. So all the acids that were arrhenius acids still meet Bronsted-Lowry's definition. The ones that are kind of added to that are the ones that contain ammonia. So ammonium NH4+ with that positive charge has the ability to donate one proton and still be a stable molecule. So you do see some acids with that ammonia group now act as a donating capacity in terms of protons. Bronsted-Lowry bases have to be able to accept the proton, so your hydroxides still are able to act as your bases, just like they were with arrhenius. But this expanded the definition of bases significantly in that ammonia can accept a proton, but you can also have polyatomic ions that are negatively charged, like H2PO4- or PO42- or PO43-, CO3-2, and HCO3-1. Those are just some examples that are capable of acting as bases now. And so I've got a picture down here showing you what happens when you drop the acid in terms of having the proton. What happens when you drop a base in, like NaOH, it produces your hydroxide, and then how your salt doesn't have hydrogens or hydroxides. As we'll see a little later, some salts, even though they may not have the hydrogen or hydroxide, because of that Bronsted-Lowry definition, they may be able to have acidic and basic properties. Monoprotic acids are acids that are only capable of donating one proton. I've given you a couple of examples over here, HF and HBr. HNO2 would also only be able to donate one proton, and this should actually be H3O+, sorry about that. This particular substance, NH4+, donates one proton and makes NH3. That, for the most part, is what you're going to only be able to see NH3 be able to do. A polyprotic acid is able to donate multiple protons, so one with like H2S, H3PO4, while polyprotic bases are able to accept multiple protons, and we tend to see those only with the polyatomics with a charge greater than -1 that can add protons up until when they are neutral. If you are amphiprotic, you can act as both an acid and a base. And so I've got an example of that down here with HCO3-, which is why it acts like a buffer in your body. HCO3-, when a hydrogen is removed from it, when it's acting like an acid, will produce carbonate ions. And then if it's acting like a base, it'll accept that proton, making H2CO3. So it can donate a proton to go back to HCO3-, and CO3-2- can accept a proton to go back to HCO3. So because it can actually make two possible substances by just either adding or removing a proton, it is considered amphiprotic. Water is another excellent example because it can make both H3O+ by accepting a proton, and it can make HO- or OH- by donating a proton. If you are a conjugate acid-base pair, you have to be different solely by one proton. So in the example down here, HNO2 and NO2-, they differ by just one proton. H2O, and this again should be H3O+, they differ by one proton. And we see that in the example below as well. To determine which one's acting as an acid or which one's acting as a base depends on the products that are formed. Here we see this acid donated a proton because now we just have NO2-, so that's the conjugate base of HNO2, the acid. Water, because the acid has to donate the proton, has to accept it, so water is acting as your base, and it accepts the proton to make H3O+. So this is what happens with a monoprotic acid when you titrate it. It will only have one of these little flat areas, and that's where all of the acid and base are used completely. It's called the equivalence point, where when you have a polyprotic acid, you'll see that you have multiple equivalence points and multiple midpoint or halfway points because you have multiple hydrogens that can be removed. pH, we talked about this a little bit in your first year class, is just the negative log of your hydrogen concentration. It could also be written as H+, H3O+, and H+ are the same thing. I will give you that equation on any quiz or exam. I'll also give you the POH equation, which is just the negative log of your hydroxide. I will not give you these two equations, which are rearranged for the concentration of the H+ and the OH-. Those two you will need to be familiar with how to get from these two equations. As we saw in our last unit, the equilibrium constant K is dependent on temperature, and for the most part our problems will be solved using the temperature at 25 degrees Celsius. So the hydrogen and the hydroxide concentration is equal to 10 to the negative 14. Very, very small, only a certain amount or a very small amount of water dissociates, and so because of that, the pH and the POH, the scale that you're most familiar with, is equal to 14. If you're neutral, the hydrogen concentration and the hydroxide concentration are equal. If the hydrogen concentration, I think I flipped it, sorry about that. The hydrogen concentration should be greater than the hydroxide if you're acidic, and if you're basic, the hydrogen concentration should be less. You should have more hydroxides present. So please make sure you switch those signs. I'm sorry I didn't catch that before now. So if you're less than 7, you have more hydrogen hydroxide, you're acidic. If you are greater than 7, you have more hydroxide than hydrogen, you're basic. And if you have equal amounts of hydrogen and hydroxide, you are neutral. So here I'm asking you, what is the pH of a 0.0045 molar NaOH solution? Well, NaOH splits into Na plus and OH minus. And so if this is the concentration of NaOH, this is also the concentration of hydroxide ions. And so if we know the concentration of hydroxide ions being 0.0045, and we take the negative log of that value, we get the POH, since we were finding it for the hydroxide concentration. However many sig figs you have in your concentration, that is how many decimal places you have when you do a logarithmic calculation for significant figures. So because this had 2 sig figs, I have 2 decimal places. And now I can use pH and POH equaling 14 to solve for the pH, 11.65. This is one way you can do this problem. There are multiple ways you can solve for it. You could have also used the hydroxide concentration to find hydrogen, and then worked your way backwards to get pH. So in this particular example, the pH of diet soda is 4.2. What is the hydroxide ion concentration in the soda? So if pH is 4.2, I can use that to find POH, which would be 9.8. And then if I take the negative log of the, 10 to the negative of the POH value, I can find the hydroxide concentration. There was 1 decimal place in 9.8, so I want 1 decimal place in my concentration value. Here I see the pH of a strontium hydroxide solution is 10.85, and I want to know the concentration of strontium hydroxide in the solution. Well, pH doesn't have a whole lot to do with strontium hydroxide, but POH is a little bit more familiar because hydroxides are present. So if my pH is 10.85, I can use pH plus POH equals 14 to solve for the POH, 3.15. And then I can use the POH to find the hydroxide concentration, 7.1 times 10 to the negative 4. In strontium hydroxide, there's 1 strontium for every 2 hydroxide ions. So if this is the hydroxide concentration, I would need to account for the fact that there are 2 OHs for every 1 SrOH2. So I would need to cut that concentration in half to get the true concentration of the strontium hydroxide solution. Okay. And I think there's just one little part left, and we're going to talk about relative strengths of acids and bases. There are some additions to your table that you have in your notes, so you may want to add things in there. I know there was one typo with an error. I think there was one word typo, so just make sure you read over this and that you're okay, that there aren't any, that your notes are accurate. For strong acids, they completely dissociate solution, which means all they do is make the ions, while if you are a weak acid, only a certain fraction will actually break into ions. Most of it stays intact. Because of this, the pH of a strong acid is usually like 1 to 2, very, very low. While if you're a weak acid, it can be anywhere from 3 up to 6, almost 7, depending on how weak of an acid you have present. So to find the hydrogen concentration for a strong acid is very different than finding the hydrogen concentration for a weak acid. In a strong acid, since it completely breaks apart, whatever the concentration of your acid was, that is the concentration of your hydrogen ions. And then you can use that to find pH. And if you notice with the equation here, we see that it's basically written in one direction because you virtually have no reactants remaining. They all split into the two ions that are formed as products. And as a result, your K is very, very large. You won't get values for strong acids for Kas, the dissociation constant, because there isn't truly a value because it just goes completely over to the products. Remember your 6 strong acids from back at the beginning of the year, the Brickle Trickle, and then the PSN, perchloric, sulfuric, and nitric acid. With a weak acid, the hydrogen concentration is very, very small compared to the original concentration of your acid. So you do have the double arrow representing the equilibrium reaction. And you would have to find your hydrogen concentration by taking the product concentrations and dividing them by the reactant concentrations. Water's not included because it's a pure liquid. And the K value this time will be very small. So depending on the size of the K value, that's going to determine how much hydrogen you're able to make. The smaller that K value, the smaller the hydrogen concentration will be. Sometimes you may have to do a calculation with pKa, and that's just going to be like pH and pOH. You just take the negative log of that Ka value. The smaller your Ka value is, the weaker your acid is. The larger your Ka value is, the stronger your acid is. And depending on the strength of your acid, your conjugate base, what's left over, so in this case Ha would be the acid, and A- would be the conjugate base. If you have a stronger acid, you're going to have a weaker conjugate base. And if you have a weaker acid, you're going to have a stronger conjugate base. And that's in part because whatever the value is of Ka, Kb will be that times the Ka value, and together they need to equal 10 to the negative 14. So if one is smaller, the other would have to be larger. In terms of ranking acids, strong acids are always going to be your at the top of the barrel, but then you're going to have your weak acids based on the Ka values. Then you would have any conjugate acids of strong bases like hydroxide, because that's not going to act as a good acid at all. And then finally, if you have no other choice, you would have water be an acid. And then the last thing I'm going to talk about is with polyprotic acids. The more hydrogens you remove, the weaker they become as an acid. So this is kind of a picture of what's going on. You see the strong acid. This is what you started with. You no longer have any of that orange left. It's gone completely over to the 2 ions. While at the weak acid, you see that some of the weak acid has dissociated, has broken into ions, but a large percentage is still intact. And then the hydrogen concentration is going to be very small compared to the amount of acids you began with. So there's another visual. You see here all the ions that are being generated, the H3O pluses and A- from your strong acid. Well, over here with your weak acid, you have one H plus ion and one A- ion, but the rest of the molecules are still the original acid. Okay, so what I'm referring to in terms of this table is the one I'm getting ready to show you. You have a copy of this Ka-Kb table. This is going to be something very helpful for you. I will give you any values that are on this chart. I would give you at least one of the two in a problem on a quiz or a test, or I would let you use this chart, but I'm feeling I'm probably not going to, since it tells you over here about what the relative strengths are. But I would like you to notice up here at the top with the strong acids, they are not assigned K values. I will not give you K values for strong acids on any sort of quiz or test because you should know that they completely dissociate. So what I'm going to do right here is fill in what the Ka values are for these different ions and substances. NH4 plus, if you go look, will be 5.6 times 10 to the negative 10th. HNO2 will be 4.4 times 10 to the negative 4th. Water is 10 to the negative 14th. That's what it'll always be at 25 degrees. C6H5CO2H is 6.3 to the negative 5th. HSO4 is 1.2 times 10 to the negative 2nd. HF is 7.2 to the negative 4th. Then HCl is just really, really large. So if I'm going to order these from strongest to weakest, I want to go from the largest value down to the smallest, which means HCl would be first, then HSO4. I have 2 at 10 to the negative 4th. The 7.2 is a larger number, so that would be third, and then would come HNO2 at number 4. C6H5CO2H would be number 5. NH4 plus would be number 6, and then when it comes to acids, water is always last. So if you were going to write these in order, it would look something like this. Alright, we have one last thing to talk about, and it's going to sound very familiar with the acid conversation we've had because it's just bases. Strong bases and weak bases follow the same rules as your strong acids and your weak acids. Strong bases completely dissociate, weak bases only partially dissociate. Strong bases completely ionize, weak bases partially ionize. Strong bases are going to have pHs like 12.5 up to 13.5, really high, while weak bases are anything greater than 7, but they don't tend to get a whole lot more than 10 or 11. If it is a 1-to-1 ratio, like an LiOH, the hydroxide concentration is your base concentration. If it is alkaline earth base, like barium hydroxide, then you would need to double the hydroxide concentration since there's 2 of them in that chemical formula. Whereas with a weak base, only a small amount of hydroxide is generated. We see the single arrow showing complete dissociation for the strong base, a double arrow for the weak base. Kb values are really large for your strong bases and less than 1, meaning that basically just the base remains intact. For your weak bases, you can find pKb just like you could find pKa. This is the part here I think where there was something off. As the Kb gets bigger, it gets closer to 1, you become a stronger base. And then depending on the strength of your base, if it's a weaker base, it's going to have a stronger conjugate acid and vice versa. And your strong bases are anything that is a hydroxide that's soluble, typically your alkali metals, and there's 3 alkaline earth metals that are soluble: barium, calcium, and strontium. Water actually can act as a better base only than the conjugate ions of a strong acid like Cl- and NO3-, but otherwise it's in the same order as we saw with the acids: strong base, then weak base, then water, and then those conjugate bases of your strong acids. Your weak bases tend to have that NH2 group, the NH3 group attached to them. So this is just kind of a chart to kind of give you some context. Again, you have that table. You see here your strong acids, and you see here the ranking of your weak acids, and water's at the bottom. Here you see your really, really weak bases, and then you see water, the rest of your weak bases, and then you have your strong base. And so you see how the strength kind of is in a diagonal opposite of one another. If you're stronger as an acid, you're weaker as a base, and that's why these conjugate bases of your strong acids actually lose out to water in terms of relative basic strength. So to order these, you're going to need that chart again, but this time we want to look at the Kb values because these are bases. So I went and got these values off of your chart. Water again is still 10 to the negative 14th. The Kw isn't going to change. So if I'm going with the strongest, I want the one with the largest Kb value. I didn't have hydroxide present, so that would be ammonia. Then I would go next, C6H5CO2-. And then after that, I would go between the 10 to the negative 11th, which one is bigger, the NO2-, and then F-. Remember I said that water is a better base than a conjugate base of a strong acid. So this is the one-time water will not be at the bottom of the list. That Cl- is going to lose out to it. And if I put them in order, that would be what I would see. Now, although I know that video was a little long, and I apologize for that, I believe now you should be able to do everything on the acids and bases worksheet for this first one. Okay?